Hello. So I'm going to try to make maybe one or two videos from 4.2, and then I'll try to make one from 4.3 to help you out with your homework. So we're still talking about compact spaces. So in 4.2, what's different than in 4.1 is that we're just talking about a topological space. So I don't necessarily have a metric in order to talk about being compact. So I don't really have like open balls, say. We're going to use sets that belong to the topology on our space. So I think how we actually defined being compact, though, it worked without worrying about a metric. So remember that's let's say xt is compact if every, or maybe if and only if, this is the definition of being compact, every open cover u, so fancy u, of x. So what do I mean by that? I mean that u itself, so I'll write this kind of parenthetically, u is equal to some collection of open sets, regular u, that live in T, so that are open sets just from my topology, such that the union of all these u's is equal to x. So such that, so the union of all u in fancy u of u is equal to x. So every open cover u of x has a finite subcover. Great. So no matter what open cover you start with, you should always be able to whittle it down to only needing finitely many. If you can do that, then that means your space is compact. So the first theorem in this section, 4.13, that's pretty important. Every closed subset of a compact space is compact. And what's kind of interesting about it, I don't think we ask you to do anything with the Cantor set, but it's a pretty famous, I don't know, object in mathematics at this level. And so in example 6, it mentions this thing called the Cantor set. And if you've never seen it before, but you're kind of interested, the book defines it in section 3.3. It's 3.3, and it is example 9. And again, this is just kind of if you're interested. I'm not going to ask you to do anything with it. So if you're like, oh, I don't care, then that's fine. You can tune out for a little bit. But if you look on it, on example 9 here, we're going to start with the interval from, I guess I won't do this here. Assuming you're looking with me here, you start with the interval from 0 to 1, and then we're going to make C1 where we just delete the middle third. So like the stuff between 1/3 and 2/3, I'm just going to take it out. And then what I'm going to do is I'm going to take that now and delete the middle third out of each of those two, and I'm just going to keep doing that. So I make all these closed sets, C1, C2, C3, and onward. And what the Cantor set is, it's the intersection of all these. So when I delete the middle third of all these subsets here, that's one way to define it. After his little picture in figure 3.4, they tell you another way to define it, which is a little bit more gross, where you're thinking about numbers as power series, where the base is 3 in a way. I'm not going to really say anything about that. Anyway, though, this Cantor set, because it is the intersection of closed sets, I know that it's closed. And so as maybe an application of theorem 4.13, is that right? 4.1, yeah, 4.13. Because the Cantor set's closed and the Cantor set, call it C, it's contained in this compact interval from 0 to 1. So like you showed me on the previous homework that an interval like this is compact, I think, or maybe we talked about it in the last video. Anyway, though, this really gross set is actually compact also, just because I know it's a closed subset of a compact space. So that's what theorem 4.13 is telling us about. That's interesting. Then it goes on to talk about being Hausdorff. And so remember, being Hausdorff meant for any 2 points in your space, you should be able to find neighborhoods of those points that are disjoint. So like if I've got this, if I've got any x and any y, there should exist neighborhoods u and v, so that u intersect v is empty. That's what it meant to be Hausdorff in a picture. You can separate those two. And so in a Hausdorff space, it tells us that every compact subset is automatically closed. So that's good to know. And then you're told, let's see, what's the next, maybe most important thing that I see? Just kind of skimming along here. Theorem 4.19. So this gets back into the idea of tie-in. What am I doing here? Sorry, you can see that. My picture of being Hausdorff, in case you missed it. So if I take any x and any y in my space, big X here, if it's Hausdorff, that means there better exists a neighborhood of x, call it U, and a neighborhood of y, call it B, so that their intersection is empty. So the next thing that's important, in my opinion, is theorem 4.19. So the continuous image of a compact space is compact. And so what that is trying to say to us here is if I've got, say, topological space xt, I'll call it tx. And then if I've got a map F that's continuous and it takes me to some other topological space, let's say T sub y. If I've got a compact subset here, call it C. So C is compact. C, compact. Then what this says is that the image of that, so F of C, which I don't know, maybe it looks like this, who knows? I'm guaranteed that that's compact also as long as my function's continuous. And so that's kind of neat. So the idea of it is if you want to show a set's compact, remember, you start with any open cover of your set here. And the idea is if I've got that this set is covered by a bunch of open sets, I want to show that I only need finitely many open sets to really cover this. And so the idea is that each of these open sets pulls back. In other words, I look at the pre-image, and because F's continuous, I know the pre-image of each of these open sets is also open. And so what that basically builds for me is the pre-image of all these sets in my cover of F of C, they give me a cover of C. And since you know C is compact, you can whittle C down to only finitely many. And so if C is covered by finitely many things, then I look at, well, what are those finitely many sets back here? What do they correspond to over here? So that means you only need those finitely many on this side as well. And so the proof gives you a much more precise way to say that, but I'm just trying to illustrate to you the idea of what's going on. Theorem 4.20, right after that, compactness is a topological property. So what did it mean to be a topological property? That means that it's preserved when you have homeomorphisms. And so if I have my same picture here, let's say that xt itself, let's say the whole space is compact. Let's say I've got a homeomorphism F. So what did that mean? That means F is bijective. That means F is continuous. And then that means I've also got F inverse that's continuous also. So again, F is a homeomorphism. Let's say homeo. So Y, I'll call it xt and yt, or damn it, tx, y, ty there. So if this space is compact and I've got a homeomorphism, we're saying any space that's homeomorphic to this guy is also automatically compact. And that's kind of a consequence of the previous theorem, but it's important enough they just call it a theorem anyway. What else? I remember one of the things in your homework that's kind of towards the beginning is they mention in number 2, they mentioned this thing called the finite intersection property. So that was actually in the previous section, but I don't remember talking with you about it. So I'll take that to do that now, take the time to do that now. So this finite intersection property business, finite intersection property, this is on page 134 in 4.1. And it's around the middle of the page, right after he talks about being countably compact. I don't need you to do anything with countably compact right now. Let's see. So what is this trying to say? So if I've got just any collection of subsets, let's say of a big set X, so fancy A here. So A has the finite intersection property. And I don't know, I'm lazy. I'm going to call that FIP. Just abbreviate this thing. What does that mean? If whenever I take finitely many members of this thing. I don't care how you pick them, but if I just randomly pick, let's number them too. Let's say A1, A2, say I take n of them. No matter how I pick finitely many out of this set, I'm guaranteed that when I intersect these, that intersection is not empty. So if these are A, I don't care how many you picked at a time, doesn't matter. But then the intersection of my sets A, 1 through n is not empty. Great. So I think on number 2, the proof of number 2, at least the way that I think you might do it, is super similar to the proof of theorem 4.5 that's right after this definition here. Maybe just think about, can you get away with kind of deleting countable from places? But I think that's a good scaffold for how your proof should go for number 2 on the homework. What else do I want to say right now? I think that might be as much as I want to say about 4.2 for right now. So I'll leave you with that.